Hello everyone, and welcome to my YouTube channel Wrong Math. Today we are going to explore one of the most popular theorems of mathematics, Pythagorean theorem. Pythagorean theorem states that in a right-angled triangle, the sum of squares of both of its legs, perpendicular and base, is equal to square of the hypotenuse. We all have learnt this statement in our middle school, and some of you might have also seen a conventional proof, which involves rearranging pieces of triangles in order to derive the equation. But that does not really explain the essence of Pythagoras' theorem, as it is a mere play of areas. It does not give insights into the fundamental reason for its existence, but not to worry, mathematics never disappoints us, and we always have other ways to approach the problem. So today we are here with another method which answers our said question, so watch the video till the end. We are going to consider a unit circle, that is a circle with radius of 1 unit. Now, considering the initial condition, that is when radius is along x-axis, we can imagine that the radius is forming a triangle with x-axis as the base, and the perpendicular equal to 0. So, here we can say by intuition that square of hypotenuse is equal to square of radius, which in this case is the base of the triangle. And hence, in this case, Pythagoras' theorem is self-evident. Now let's rotate the radius to some angle x, and then increase the angle by a small value dx. Now we will compare the sum of the squares of these two triangles. Consider the case at some angle x, sum of squares of two legs of right-angled triangle is OA square plus AB square. Now, we will rotate the radius further by some angle dx, and we'll consider the triangle OCD, and we'll write the sum of square of legs. The idea is to prove that the sum of squares of the perpendicular and base remains constant even if we change the angle. That way we can show that the sum of the squares of the sides is always equal to the hypotenuse square. As angle dx is infinitesimally small angle, arc BC can be considered to be a straight line. Also, the length of arc BC is equal to radius of circle multiplied by angle subtended at center. So, the radius of circle is 1 as we are considering unit circle, and the angle subtended at center is dx. Hence, BC is equal to 1 multiplied by dx, which is equal to dx. Now we draw a line parallel to x-axis through B and say it intersects CD at M. As line MB is parallel to x-axis and alternate angles are equal angle MBO is equal to angle BOD is equal to x, CB is perpendicular to OB. Therefore, we can say that angle CBM is 90 minus x, and angle MCB is x. Now consider triangle CMB and OAB. These two triangles are similar to each other because all the three angles of these triangles are equal to those of the other. By using the property of similar triangles, that is, ratio of corresponding sides of two triangles is equal, we arrive at the following equations. 1 upon OA is equal to dx upon CM, and 1 upon AB is equal to dx upon MB. Solving equation 1, we can write CM is equal to OA dx. Solving equation 2, we can write MB is equal to AB dx. Now CD can be written as CM plus AB, putting value of CM equal to OA dx. So we get CD is equal to AB plus OA dx. Similarly, OD can be written as OA minus AD, where AD is equal to BM. So OD is equal to OA minus BM. Putting value of BM is equal to AB dx. So we get OD is equal to OA minus AB dx. So now as we have the value of OD and CD, we can write the sum of squares of legs as OD square plus CD square equal to OA minus AB dx whole square plus AB plus dx whole square. Now we can represent this as area of two squares, one of which has sides OA initially, and then we reduce AB dx from both the sides of square. The resultant smaller square represents the value of OD square. Similarly, the other square initially has side AB, and we increase each side by OA dx. The resultant bigger square represents CD square. Now, interestingly, we observe that the area we have reduced in first square is what we have added in the second one. So the net result of their addition is OA square plus AB square. One important thing to note is that we have ignored those smaller squares at the corners AB dx square and OA dx square as they involve square of dx, which is a very small number and is generally ignored. Alternately, you could have analyzed the same by using algebraic identities and opening the square and adding the terms OD square plus CD square equal to OA square minus 2OA AB dx plus AB dx square plus AB square plus 2OA AB dx plus OA dx square equal to OA square plus AB square. Interestingly, this is what the sum of squares of the two legs was when angle was x. So when we change the angle from x to x plus dx, the sum of squares of two legs remains same. So, any change of angle from x1 to x2 can be viewed as changing the angle in infinitesimal steps. And as we have proved earlier, changing angle by dx won't actually change the sum of square of the two legs. So, changing angle from x1 to x2 won't change the sum of squares of legs. So we can conclude that sum of squares of perpendicular and base remains same. Now going back to the initial, which we derived when angle with x-axis was 0 degree. In the initial case, we proved that sum of square of perpendicular and base is equal to square of radius, which is actually the hypotenuse in the discussion. Hence, sum of squares of perpendicular and base is constant and is equal to square of hypotenuse. This is what Pythagoras theorem states. So we have that sum of squares of perpendicular and base is equal to square of hypotenuse. We have done this proof by using unit circle and basics of geometry. Hope you liked the approach and the video. For more such interesting ways to learn new approaches to mathematical problems, hit the subscribe button and stay tuned with us.